Good morning. All right. Just a couple announcements before we start. So next week on Tuesday, there'll be the psychology department's running an online symposium. This will be a lot of it will be people presenting their research, undergraduate students in the department presenting their research. There'll be panels, grad student talks, talk from Tori Higgins, and so yeah. So I encourage everyone to join. Um, I'll remind people on Thursday as well. So yeah, we're heading to the end of the class. This will be the last lecture with things you'll be tested on. There'll be the final lecture on Thursday, where we'll be talking about applying techniques in the class to the ongoing coronavirus research. The final project is out on Thursday and due the following week. Yeah, there's a question in chat about does the fact that you have a whole week mean that it's a lot longer than projects 1, 2, and 3? It's intended to be a little bit longer, but it's definitely not intended to take you the whole week. It's maybe something like 20% longer than the other projects. It does cover material from the whole class, so it's more challenging in the sense that some of the things you'll be doing in there are things from the earlier projects or labs. But it's not intended to take that full 7 days. Um, yeah, so I'd recommend that you try to have everything else turned in this week if you can before you start the final project. Again, that project is going to cover all the material from the class. But at the latest, please try to have everything in by the end of next week. We have to have grades in at least for some people by the 15th, and so I want to give the TAs at least a week to get through the backlog of everything. So yeah, so please try to aim for having everything in by the end of next week. If that deadline's not going to work for you, just send us an email. We can figure something out. But I'm hoping that at least the bulk of the stuff we can have done by then. All right. Any other logistics questions? All right. So today's class, we're going to step back a little bit and think about some of just the main lessons from the class. And we're also going to think about a strategy for how we actually decide what kinds of techniques to apply to what kinds of problems. So almost anytime we're doing something in science, we're going to be doing some kind of quantitative analysis. Even when we're doing things qualitatively, we're often trying to develop hypotheses that we could test quantitatively. And there's many different kinds of questions that we ask in science, and so there's many different kinds of analyses that we do. We might want to just compare two separate groups or more than two groups. We might want to measure associations between different kinds of variables. We might want to measure how predictive particular models are. How well does one piece of data predict some other piece of data? And so with all these different questions, they all correspond to different kinds of statistical analyses we could do to try to answer these different questions. The field of statistics and applied statistics is enormous. We've talked about a big chunk of it in this class, but there's much more of it. There's much more of it that I don't know. That's really many pieces of statistics are really sort of specific to specific fields and the specific challenges that they try to deal with in understanding their data. And so what that means is that there's basically no way to know all of it. For people that are working in scientific research, you basically have to just continuously learn about statistical methods. For example, a lot of graduate school is basically trying to understand new research techniques and including statistical research techniques. Right. And so there's a lot of challenges here. One is that our data never meets the assumptions of these tests we're doing. I mean, even the most assumption-free things we've talked about still require things like independent random samples, which we never have. And so in some cases, these assumptions are sort of close enough to true that we can use these methods. And other times they're not, that for the particular kind of data we're collecting, we actually need to care about these violations of these assumptions and think about methods that can deal with them. So we end up, when we're studying these methods, trying to answer a few different questions, right? And what we want to think about is what kind of strategies can we use to try to get conclusions out of data. And conclusions can mean testing different scientific theories. It could mean getting actionable information that we could use to make a decision. And we want to think about not only the data that's coming out of experiments, but how are we designing experiments in the first place? And there's this ongoing balance between using complex, sophisticated tools and having those tools actually be interpretable. Right. And there's sort of a danger of if we use a tool that's too simple, it's not going to really capture the features of the data that are important, that we care about. And if we use models that are too complicated, we might not be able to understand the actual predictions that come out of them. Okay, so for a lot of the class time today, we're going to think about the fact that we've talked about many different kinds of tests in the class. And so we're going to try to think about organizing them into some way that we could actually make decisions about which ones we want to use. So there are some just conceptual distinctions, like between descriptive and inferential statistics. But really, I'm talking here about just the inferential tests, right? How do we organize all these inferential tests that we've talked about? And so one way to think about this is to make what's called a decision tree, which is just basically a series of questions we can ask ourselves when we're trying to analyze data that can tell us what kind of test we should be using. Right. What we need to think about is what are the key features of the data set that we're trying to explain. And then we can narrow down by process of elimination what tests might be useful for this data. Ideally we'll end up with just one remaining test here. This might not always be the case. It might be that we're going to end up with multiple possible tests we could use. And then we have to think about, for example, what kind of assumptions we want to make from our experiment. For some kinds of tests, there might be computational trade-offs that maybe running a full permutation test for this data set is going to be too slow, for example. Okay, so the first kind of decision we have to make when we're trying to analyze data is thinking about what kind of variable we're measuring. So, right, and this goes back to some of the very beginning weeks of the class when we talked about nominal, ordinal, and scalar variables that we can measure. And so when our data is scalar, we can employ parametric tests, meaning that we can employ tests that test for things like differences in the means. These parametric tests means that we're using tests that use parametrized distributions. Right, that there's some kind of outcomes that we're measuring. These outcomes fall on a continuous scalar line, and we're trying to describe something about, for example, where these outcomes would be if the null hypothesis were true. When our data are ordinal, then instead we switch to these non-parametric rank-based methods, right? So that instead of actually trying to capture the distribution of these data, we are only interested in their ranks, right? And we can still do tests on the medians, right? But here we're thinking only about the distributions of the ranks and not about some parametric distribution of the actual data. And finally, we also have some options, even if we only have nominal outcomes, right? So we can do things like chi-squared tests if the outcomes we're measuring are simply one of several possible outcomes that can't be ranked in any way. Okay. So in some kinds of data sets, this might be all that we have, is we're just measuring some kind of outcome. But usually we're also measuring something else about each person in our experiment, which is something we're calling a predictor, right? And this predictor could be a lot of different things depending on the situation. Ideally, if we're running a true experiment, this predictor should be something that we're manipulating in each person. Right. So, for example, we're assigning people randomly to groups, or maybe we're parametrically varying the difficulty of the task that they're doing in some way. In a lot of other cases and a lot of observational or quasi-experimental settings, this predictor is just going to be something else we're measuring about each person that we don't have full control over. And so these predictors could be groups, which would be a nominal variable, right? This just means that people are either assigned to one of several groups, or they're telling us which group that they fall in. Our predictor could also have an ordering. So if it's a ordinal predictor, we could do some kinds of regression. If it's a full scalar predictor, then we can do things like Pearson correlation and the kinds of regression we talked about in this class. Okay, so then another kind of breakpoint on this decision tree is thinking about how many groups we need to compare. So when we have only two groups, then we're going to be usually doing something like a t-test or a non-parametric version of a t-test. When the data belong to three or more groups, then instead we're going to have to use something like an ANOVA, right? And these two kinds of tests are somewhat different, right? The t-tests are directly looking at something about the distribution of the difference between the groups, whereas the ANOVAs are instead set up in this analysis of variance framework, right? Where we're trying to see if knowing this group information decreases our uncertainty about the outcome. And then finally, probably the hardest part about picking a test is that we also have to think about the assumptions of these tests, right? So once we've gotten down to which tests are appropriate to apply to our data at all, just in terms of the type of the data, then we'd have to think about which of these tests that we're left with, which of these assumptions actually match assumptions we're making about the data. And so, yeah, I'm not on chat there. Can you clarify the independent var groups? What you mean by that? Yeah. Oh, sorry. Yeah. So the independent variable is usually in an experimental setting. The independent variable is usually going to be the groups that we're assigning people to. It doesn't have to be. I guess there are also situations where right. Yeah. So the number of groups here is going to be usually the it can be an independent variable we're assigning to people. There are also cases where these groups could be a dependent variable. And so, so you could have categorical outcomes from these. So if you, so maybe we're like giving people different doses of a drug. So that's a continuous independent variable. And then the outcome is like some kind of categorical thing. Like, was this person hospitalized or not? Or did this person go into remission or something, right? So it could be that the groups here are, we can have categorical outcomes here, right? That are the dependent variable. I've brushed over this a little bit because we haven't talked in this class about one of the main methods for doing that, which is called logistic regression, which we haven't talked about, but that's a way of doing a regression where the input variable is continuous and the output variable is a nominal outcome. So yeah, so you can definitely do that, and there's definitely situations where that makes sense. Okay, so so this final kind of hard decision to make is about the assumptions of the test, and this really requires you to have some kind of expert knowledge in the domain you're studying to know which of these assumptions make sense, right? So is this assumption of normality, is assumption of normality in the distribution, does that make sense or not? Again, it depends on the thing that you're measuring, if that makes sense. Do we have worries about whether the variance might be wildly different in different groups, right? Remember, the sort of rough order of thumb for ANOVAs is if there's a difference by a factor of more than 4 or something, then in the variances, then that's going to lead to invalid p-values in the ANOVA. We also have to worry about things like, is this sample size big enough? So for some of these tests, like the chi-squared test, for example, assumes that these statistics are obey the central limit theorem, and so that'll only hold if our sample's big enough. And then maybe one of the most challenging assumptions here is about how was the data sampled, and was it close enough to random independent samples that we can make that assumption. Okay, so putting all this together into a single slide, we can have this decision tree of basically all the different paths we could take in this among these decisions. So the first split in this decision tree is what is the thing that we're measuring? What's the outcome that we're measuring? If it's a nominal outcome, we're going to go down this path of basically this chi-squared path. And so if remember, there's two different kinds of chi-squared tests. So one possibility is that this thing that we're measuring a single variable, and we want to test whether it matches some kind of null distribution. Right, so we're rolling a die, for example, and on every roll of this die, we get one nominal outcome. And what we want to know is, are these nominal outcomes coming up equally likely, something like that. Right, for this, we could use a one-way chi-squared test, which is our test of whether the frequencies of these nominal outcomes, right, our counts of these nominal outcomes, are they consistent with some kind of null distribution? If we're measuring two different nominal outcomes, we could also do an independence test, right, to test whether these two different outcomes are related to each other or not. And this is a two-way chi-squared test, right? Here, our null hypothesis is that these two different outcomes are not related to each other. We can construct this expected frequency matrix under that null hypothesis and check to see if it looks like that's a good explanation of our data or not. Okay, so this is one branch here, is these nominal outcomes. Another kind of outcome are ordinal outcomes, right? So these are things that we're measuring that are ordinal variables. They could also be scalar variables that we want to treat as ordinal because, right, maybe the distribution, for example, is very non-normal, or maybe we think that the absolute value of these numbers isn't really that important, and all that matters is the ordering. So if we're measuring an ordinal outcome and our predictor is also something that can be ordered, then we can do things like a Spearman's correlation, right, to check to see if the ordering of our predictor matches the ordering of our outcome. The people that are on the low end of the predictor, are they also on the low end of this outcome? We could also look if we have groups, if we're trying to compare ordinal outcomes across multiple groups. Then for two groups, we would use a rank sum test, which remember is the kind of rank version of a t-test. Or we could use, if we have three or more groups, we could use a Kruskal-Wallis test, which remember is the kind of nominal version of an ANOVA. Right, so there's our ordinal branch, right, that we can basically, for this ordinal outcomes, we can either look for relationships with some kind of rankable predictor, or we can just look at differences across groups. Okay, and then the biggest branch here is scalar outcomes. This is probably one of the most common things we're measuring. If we're in the case where we have scalar predictors as well as scalar outcomes, then we're in kind of correlation and regression land, right? So we can measure Pearson correlation between these predictors and these outcomes. We could also look at regressions. Regression's also especially useful if there's multiple predictors that we're interested in. Okay, or this other branch here is nominal predictors, which means that we have some kind of scalar outcome divided among multiple groups. And these are, again, could be groups that we assign people to, or just some other nominal information we're measuring about each person. One possibility is that we're getting independent samples, meaning that we're getting a single measurement from each person, like at a single time point. And the simplest case is that there's only one factor, meaning that we're measuring a single nominal group from each person and an outcome from each person. And so if that's all we have, then we can do a one sample t-test. We could use a z-test if we know the population variance, although that's pretty uncommon. Right, so one sample t-test is just testing whether this distribution of outcomes in this single group matches some kind of null hypothesis. Or we can compare multiple groups. So we could do an independent samples t-test if we want to compare whether two different groups have the same distribution of scalar outcomes, right? We're specifically testing here whether they have the same mean of their scalar outcomes. If we have three groups, then we have to go into ANOVA land, which most of the time would just be a regular ANOVA. If we're worried about this assumption of equal variances, we could go to a Welch's ANOVA. right? And so all of this whole section here is all about testing among groups where we have a single factor. We could also have multiple factors, which means that we have multiple nominal predictors for each person, in which case we have to go into factorial ANOVA land. There's one last chunk of this plot here, which is about repeated measures. So this is cases where we get multiple measurements from each person. This might be, for example, before and after we do some intervention, or maybe we assign each person to two conditions and we get measurements from multiple conditions for each person. So in the simplest case where there's just two groups with normal differences, and here the groups here is the same people that are in one condition and then in a second condition. And as long as we assume that the differences between these two conditions are going to be normally distributed, or at least the sampling distributions of their means are normally distributed, then we can use a paired t-test. Remember, this is basically identical to a one sample t-test. If we're worried about the differences not obeying this assumption, we could switch to this non-parametric version, which is the Wilcoxon test. And finally, if we have repeated measures from multiple groups, we can use a repeated measures ANOVA. Right, this is a case where we have multiple measurements from each person, so we're looking at differences, but we have more than two groups. So we have people that are in multiple conditions, and we have multiple measurements from each person. So this lays out almost all of the tests we've talked about in the class, right, and when you would use them. The one thing I haven't talked about is actually the first stuff we talked about in the class, which is that we don't actually have to go down this tree at all. And it might be that no route on this tree works. So for example, maybe we want to test for a difference in means between the two groups, but the data doesn't satisfy the assumptions of a t-test, for example. So we can always go back to our backup plans, which is the first things we talked about, which are just brute force. Good guess on chat there. Just brute force, just construct a null distribution from scratch by ourselves, right? So what that would mean is things like just take our group labels and permute them and see what the distribution of our statistic looks like. If we have some simulation of what our null hypothesis says the data should look like, right? We can generate from that, we can sample from that null simulation and see what the null distribution should look like, and then get a p-value that way, right? See how often in this generated brute force distribution, how often do we get values at least as extreme as what we actually saw in our data. We can also do this for confidence intervals, right? And here, instead of having broken data that we're either simulating from the null distribution or purposefully breaking our data with permutations, instead here we're doing this resampling from our data, right? Which is basically just testing to see how sensitive our results are to this exact data set. So if we resample, if we jiggle our data set a little bit, how much do our results change? And if they change a lot, that tells us that we don't have a lot of confidence in the answer. So there's lots of advantages to these brute force things. One is that as long as your data set isn't like super tiny, these will basically always work, even with super crazy analyses. So like a lot of things that my lab does, we are using like these machine learning things that would be pretty much impossible to model parametrically. Like the stuff that goes on inside of them is very complicated to reason about. And so we rely a lot on these kinds of methods. And so, the question is, why not just always do this? So the answer used to be computation power, because, especially if you're trying to estimate a really small p-value, you might have to measure like 1 million of these permutations. Nowadays, that's usually not true. For some very complicated models, it is still a problem to fit them this way. Right, so doing this bootstrap analysis, for example, requires us to rerun the whole analysis pipeline on each of these resampled data sets, which can be a bit of a problem. Like some of the analyses that we do with fMRI data might take like 3 hours to run. And so we don't want to run them 1 million times because it'll be really slow. So that's one issue. There's another, there's a worry about whether we can understand them, although it's not necessarily a problem. I mean, they're going to generate a null distribution, and so we can just look at that what that distribution looks like. Um, Another reason people don't do this is that if your data does match the assumptions of one of these parametric tests, then it's sort of a lot easier to communicate to people what you're doing, right? If the data matches the assumptions for a t-test, then just using a t-test is easy to explain to people what you did. It's easy for someone else to recreate it on their end without writing a lot of custom code or anything. So some of it's just sort of like a way of simplifying what our null hypothesis is. And then, yeah, and to be honest, a lot of it is also just like tradition that a lot of people are not familiar with these methods. Most intro stats classes don't talk about permutation tests. And so that part of it is, I think, just some inertia in the field that people don't use these. But I think it is good to understand when you can use the parametric tests, right? When you can use them, they can basically tell you exactly what the null distribution looks like. Anytime you go to these brute force methods, you're never getting an exact null distribution anymore, right? You're always having to deal with estimating these things. Okay. All right. Any last questions about decision tree stuff? Okay. So what I wanted to do for a bulk of the class today is go through some examples. So we're going to talk through 6 different experiments, which are things that psychologists might do. And for each of these, I'll read through the description and then show you the tree and give you some time to think about where we should be on the tree. And then you can type into chat what kind of test you think would be appropriate here. Note that for at least half of these, there's going to be multiple possible answers, depending on the assumptions that the researcher is making. So you'll see sometimes it might be hard to actually know which path to go down in the tree, but in general, most of the tests are not going to be applicable to most data sets, right? Most of the time, there are decisions about like whether our outcome is scalar or nominal, for example, that are relatively easy to make. Okay, so then after you give your answer, then we'll talk through the possible answers together. And again, there might be more than one. Okay. All right. So this will be basically like a very kind of extended quiz with a lot of examples. Okay, so first example is there's a researcher that believes that the recall of verbal material differs with the level of processing of that material. And so we have people that are divided into 3 different groups. A low processing group, which means that people, they're given each word and they just have to count the number of letters in the word, right? And so our hypothesis here would be that this is a very low amount of processing of the word. They don't even really have to look at the word. They just have to look at the letters. We put some people in a medium processing group where people have to look at the word and think of a word that rhymes. So this requires at least thinking about the word a little bit. You don't have to think about its meaning, but you do have to think about at least something about its phonetic structure. And finally, a high processing group where we explicitly tell people, please read this word and try to memorize it, right? So these people are hopefully thinking a lot about the word and trying to think about a way to fit it into their memory. So we have people read these 30 words 3 times in one of these 3 groups. And then we ask them to recall as many of the words from the list as they can. And our outcome here is we're counting how many words that they're getting from how many words they're correctly recalling from the list. So what we like to do is test our hypothesis here, right? We want to know, does manipulating the amount of processing that these subjects are doing on these words, does it have an impact on their later recall? And the question is, what kind of statistical test would we recommend that the researcher use? Okay, I'll give you a few seconds to think about where we should be on this tree. All right, so remember here, we're measuring how many words people are recalling. We're assigning people to one of these 3 possible processing groups. And so where should we end up on this chart? Yeah, this is the this is the first time going through here, so it's maybe a little bit challenging. Um, and and again, there's multiple possible right answers here depending on the assumptions that we're making about each of these outcomes and what we think is relevant. So so I think in general this would be in a scalar outcome category, right? So we are so here the thing we're measuring is the number of words people are recalling. That seems reasonably scalar in the sense that right, every additional word they recall seems like extra information, right? So we'll probably go down this path. And our predictors here are the groups, right? People are in 3 different groups. So these are nominal predictors. We're only getting one measurement per person, right? So we're in independent samples land here. Every sample is an independent draw. So now let's see. So there's some disagreement in chat about where to go next. So there are 3 groups here, right? But there's only one factor, right? Which is that the factor is which of the processing groups you got assigned to, right? This is a common source of confusion here about factors versus levels of the factors, right? So every person is being assigned to exactly one group, and there's 3 different choices of those groups, right? But factorial ANOVA is a case where there's multiple nominal things we know about each person, right? So maybe we assign people to a group, and then also within those groups, maybe some people get a short amount of time and some people get a long amount of time or something, right? So that would be a factorial ANOVA, is that there's 2 different manipulations we're doing. But here this is just one factor, right? With 3 possible levels. So we're down in this corner here. So then, we have a final choice here about whether we want to do an ANOVA or Welch's ANOVA. Probably like the default thing here, what people would do would be an ANOVA. But if we had reason to believe that the variance is going to be really different in these groups, then we might need to go down this path to Welch's. Here it's not super clear. Like I said, the sort of default is ANOVA because people are more familiar with that. Welch's ANOVA has pretty good power efficiency. You don't lose that much by going to Welch's, and then that way we don't have to make this assumption. So I might prefer Welch's here because especially in the high processing group, we might expect a lot of variance across people. Some people are much better at memorizing these random words than others. So it's a little hard to say, but I think you could make a pretty good case for any of the ANOVA options. Let's see if the screen's looking blurry. Things seem mostly okay on my end. Let me know if that doesn't get better. I could like refresh the thing that's streaming here. Okay. All right. So let's do another example. So a researcher is interested in testing 2 interventions designed to reduce racist graffiti in an inner city area. Recruited 10 neighborhoods that have a problem and asked assistants to provide measures of the square feet of new racist graffiti each week. So we're getting a measurement here, right, every week from these different neighborhoods. So after 4 weeks of baseline recording, they're going to do an intervention, which is a sensitivity training workshop in half of the neighborhoods. And they're also testing an advertising campaign in the other 5. Right, so they're randomly assigning 5 of the neighborhoods to one intervention and another 5 to a different one. And their community members are continuing to measure how much new graffiti there is every week. So we end up with, for each of these 10 neighborhoods, there's 10 different measurements for prior to the interventions and 6 afterward. Right, and what we want to know is, did the interventions help? Right, did they help relative to the baseline, and also was one better than another? Okay, so let's think about where we should go on this plot. So, right, we're measuring here is the square feet of graffiti that's of new graffiti that's being measured every week. And we have these communities that are being assigned to one of 2 possible interventions. And we're taking measurements over 10 weeks, right? Starting from before the interventions and ending after the interventions. So where should we end up? So let's see. So we can think about the first branch here, right? So we're definitely in we're at least most likely going to be in scalar outcome land, right? We're measuring something that's like a number, um, and so right, this is the square footage, so it probably makes sense to go down this route. Um, our predictors here are the right, which intervention people are getting assigned to, right? So these are nominal predictors. And we're getting lots of, and so yeah, we're getting lots of measurements from the same communities. So we'd be over here somewhere in repeated measures land. So yeah, so it actually, where we go from here depends a little bit on what hypothesis we want to test. So I think at least the simplest way to go would be down here into two groups land, which is that we have weeks before the interventions and weeks after, and so right, we're looking for we're just going to get like a difference. We're going to get sort of a bunch of measures of differences, and we have the two different groups, which is the two different interventions, right? And so we'd be potentially either here in a paired t-test if we're just looking at how much change there was in each group. Probably Wilcoxon is probably a little bit better here. Like the amount of change is almost certainly going to be a really weird distribution. For example, the amount of graffiti can't be less than 0. So it kind of depends what the distribution looks like. But like if at least if there's some weeks with zeros in them, then this distribution is going to be kind of the amount of improvement can't be like a super normal thing. So yeah, so I think Wilcoxon probably makes sense. I think you definitely could also make an argument. I don't have it on here, but for repeated measures, ANOVA, for like, this would be sort of a repeated factorial ANOVA, which is that if we think there's an effect of week as well as an effective intervention, right? So maybe there's something overall that's happening in the community or the country over this 10-week period. And so we might actually have, in addition to the thing we're manipulating, which is these two groups, there's this other factor, which is what week of the year is it, right? And so if we consider that there's actually this second factor that we're not controlling but is important for our data, then we'd be in repeated measures ANOVA land, right? This would be like a repeated measures factorial ANOVA, that there's both weeks happening and interventions, right? So again, it depends a little bit on our assumptions where we would end up here. I think, yeah, at least the simplest thing would probably be some kind of Wilcoxon test, just to say, are these interventions having an impact, and is there a difference in how much impact they're having? Okay. Yeah, these are intended to be kind of tricky. And like I said, there's not even exactly a right answer for all of these. A lot of this depends. We really would have to know more about the domain, and we'd have to know more about the data to make a better recommendation to these people. Okay, here's the third example. So a psychologist wants to investigate the relationship between stress and mental health during the first year of college. So the researcher developed scales to measure stress, measuring the frequency of stressful events, the importance of these events, the desirability of the events, and the impact of these events. And the researcher has 150 first-year college students fill out this questionnaire to measure this amount of stress, as well as a symptom checklist to measure mental health. And so it's designed to assess the severity of the mental health symptoms that the student is experiencing. And so the question is, how would we test their hypothesis, right? We want to figure out if the number of symptoms that a student is having, is it related to this stress that they're experiencing, right? So yeah, so let's think where to go on this plot. So right, the outcome here that we're trying to predict is this mental health symptom scale. And we're trying to figure out whether knowing the amount of stress that someone's going through, right, does that help us predict where they're going to fall on this mental health symptom scale? So yeah, so where do we go here? Yeah, it's a good question. So I think Yeah, here I'm just thinking about this as just stress. So we're trying to get some measure of over the first year how much stress are they experiencing is what the goal of the survey is, and then we're also trying to figure out over the first year what's their score on this mental health symptom scale. So yeah, so I think there's definitely there's a few different possible answers here. Um, yeah, I think probably the first thing we would try would be to treat this mental health scale as a scalar outcome, right? So we're going to measure like how many symptoms does this person have, and we can just like count them. Maybe there's some kind of scoring for severity here, right? But there's some overall score of symptoms. And the predictors are also scalar, right? Which is like how many stressful events are they experiencing, right? Or we have some overall like stress score for this person, and we can just look to see if they're correlated with one another, right? So can we predict the amount of the amount of symptoms someone's having or the severity of their symptoms based on some kind of scalar predictor? Um, we could also potentially, depending on what we think what kind of properties this scale has, we might actually treat this scale as an ordinal outcome. That right, it might be the case that like the exact value that you score on this scale is like has a really weird distribution, which is often the case for these kinds of scales, right? So it might be that someone that is experiencing very little mental stress is scoring very low on these. But if you do have some kind of mental health diagnosis, then you may be getting like enormous scores on these, right? Like maybe every single question applies to you, and so there's this extremely long tail. And so it might be the case that we don't actually care about like the exact number. It's not that a score of 100 is 100 times worse than a score of 1, right? But we can say a score of 100 is worse than a score of 1. So maybe we are actually in this ordinal land where we just want to know which students are experiencing the most symptoms, right? Regardless of exactly what score they got. And so then we'd be here in more like Spearman's correlation, right? Just asking, can we, based on their stress score, can we predict where you're falling on this spectrum of sort of experiencing the least mental health symptoms to experiencing the most without caring about we're not trying to predict your exact score. We probably wouldn't be down anywhere in t-test or ANOVA land here, right? Because we don't have people aren't in nominal groups, right? That we're not assigning people to like a low stress and a high stress condition. You could think about dichotomizing the predictors here. So instead of having this continuous stress score, we could just break people into a low stress and a high stress group, in which case we would be down in nominal predictor land somewhere in, so for example, somewhere in like a independent sample t-test, right? So are the people that are low stress, do they have different kinds of mental health outcomes from the people that are high stress, for example, right? And so again, whether the way we dichotomize these things might depend on the properties we think we have. We could dichotomize both, so we could have people in low or high stress groups as our predictor, and then we could have people in like low or high mental health symptoms as the outcome, right? And then we'd be up here in like chi-squared land, right? So again, it depends on the properties we think that these tests have. It also maybe depends if we want to build a predictive model. It also depends what kind of things we want to predict. Do we want to be able to predict a sort of more sensitive measure of people's severity, or do we just want to figure out like, is this student someone that we should reach out to for counseling or something, right? We just want to make a binary decision. Okay, here's example number 4. So a psychologist is interested in comparing the demographics of grand jury members to the demographics of the population to see if jury panels are really representative. And so the first variable we're going to look at here she's looking at is age. And so she gathers her data. And so in this community that she's measuring from, the overall percentage of people in this community over 65 is 25%. But out of the 200 people that are in her jury data set, 38% of them are age 65 or higher. Right, so there's this baseline measure in the population, which is 25%, and then in the particular sample of 200 people here, 38% of them are over 65 in these juries. And what she wants to know is this surprising or not, right? The fact that 76 out of the 200 people on these juries were over 65, does that indicate that there's some kind of non-random sampling happening here, right? Does that indicate that the whatever the population of people that is polled for juries is not the same as the overall population in this community? Okay. So, right. So the data that she has is out of these 200 people that were on recent juries, she knows whether or not they were over 65 years old. And what she wants to know is whether the number of people that were over 65, is that surprising given the population that this jury is supposedly representative of? All right, so the first thing to think about here is what kind of outcome we're measuring. Right. So there's actually, well, I guess it depends on exactly what the data is. If we're thinking about age as the outcome, then we would be down in scalar outcome land. But the way that this researcher is setting up her hypothesis is just interested in whether the number of people that are over 65 is different or not. Right. And so if we're only thinking about this, right. So I think we're assuming here that she's just thinking about this in terms of like binary demographic categories, right? Is this person over 65 or not compared to the population? There's questions about whether you can use Bayesian stats here. And in this example, let me think. I mean, you certainly can do you definitely can construct a Bayesian model for this. We haven't talked in this class about how you do that. You basically would need to, we haven't talked too much about how you do this, but you would, it's related to this concept of logistic regression I mentioned, which is that you would basically need to have a kind of probability distribution that has binary outcomes here of whether or not you're over 65. You need to have some kind of prior about how likely we think that they are to be under 65, which we have from our population. And then you'd also need to have like a Bayesian description of the sampling process and things. But you can definitely do a Bayesian version of this as well. Okay, so let's think about the answer here. So I think, at least the way that this was set up in the question, the only outcome we have is this nominal outcome of whether is this, for each person on the jury, we're figuring out whether they're over 65 or under 65. And we only know this one thing about each person, and we're trying to compare it to some baseline in the population, right? So that takes us down into a one-way chi-squared, right? So what we're trying to do is figure out, we have this nominal outcome from each person, which is, are they over 65 or not? And in this in this sample, there's 76 people that are, and 200 minus 76 people that aren't. And we want to know whether that's surprising given the baseline rate of 25%. In this particular case, since there's only two outcomes, you also could use a binomial test here, which we talked about a while back. In this case, a one-way chi-squared test with two groups is also the same thing as a binomial test, right? But you can just call it a chi-squared test. All right. Any other questions on that one? Yeah. Some people did t-test, which would make sense if we were looking at the whole age distribution, right? So if we had for each person their age as a scalar number, then we could try to compare. If we knew, for example, the mean age in the population, we could look to see if the mean age of the juries is different from that or not, right? The specific question that this researcher was asking was more focused, which is just asking whether, senior citizens over 65, are they overrepresented in juries or not? Okay. All right, we've got two more of these. Here's number 5. A psychologist is interested in whether or not handedness is related to gender. So she wants to know if the percentage of left-handed men in the population is different from the percentage of left-handed women. Right. So is there some relationship between being left or right-handed with people's gender? And so she's collecting data on handedness from 400 people, 200 men and 200 women. So what kind of test would she use to test her hypothesis, right? What she wants to know is whether there's some relationship between the two of these. Is your chance of being left-handed, does it depend on your gender or not? All right, so let's think of where we would need to go here. Right, so you want to think about how many things are we measuring from each person, and what kind of variables are they that we're measuring? So we think we're measuring two different things here from each person, right? One is one thing we're measuring is we're asking them to report their gender, and then the other thing we're measuring is we're asking them to report their handedness, right? So we know two things, so that knocks out all the like one factor, one group stuff here. And so, and for each of these things, they're just nominal, right? So we're just asking people to pick one of two possible nominal genders. We're asking people to pick one of two possible handedness, right? And again, on the research, depending on the research questions you're asking, both of those may be good or bad ideas, right? We may be interested more in gender spectrums. Maybe we're interested in handedness spectrums. Like some people might be sort of prefer one hand but could use either, right? Or maybe equally prefer both, right? But at least the way that we're specifying it here, both of these are binary outcomes. And so this takes us down into nominal outcome land. And since we're measuring the relationship between two different things, that takes us over to 2A chi-squared, right? So for every person is going somewhere in a 2x2 grid, right? There's 4 possible outcomes here of the combinations of gender and handedness. We just want to know whether those two things are related to each other. Those two different nominal outcomes are related to each other or not. Yeah, in this case, this is really the only test we could use here. If we don't satisfy the assumptions for the chi-squared test. So for example, maybe there's very few left-handed people in this sample. And so some of our, like the number of left-handed women is only 2 or something. Then we may need to fall back on things like a permutation test that, the null hypothesis there might not actually follow the true chi-square distribution. We might have to fall back on a permutation test. I should say too, also like in R, for example, if you try to run a chi-squared, that doesn't satisfy the assumptions of the test. So for example, the number, you have some cells that are close to empty. It'll actually just run permutation tests for you. There might also be like an argument you could tell it which one to do. All right, last one. So a researcher is interested in the relationship between SES and domestic violence and believes that there's a greater incidence of domestic violence in households with lower incomes. So to assess this, she surveys a random sample of adults and is asking 2 questions. From each person, she's asking them to estimate their household income, and then is just asking them a binary question of whether there's been any physical violence between members of their household, yes or no. Right, so there's 2 questions on the survey. One is estimate of household income in dollars. The second one is this yes or no question about physical violence. And the question is, how could we test this hypothesis, whether there's some relationship between these 2 things that they're measuring? Obviously, we couldn't say here whether this is a causal relationship, right? But just whether, based on this observational data, there's some relationship. All right, so where would we end up here? So remember, we're measuring 2 different things. Oops, an arrow disappeared from this plot, but we're measuring 2 different things for each person, right? One is income and one is whether there's been physical violence. And then we want to know whether there's some relationship between those 2 outcomes. So I think when we're thinking about this, I think the best way to think about this is that based on the hypothesis that she has, that the outcome here is whether or not there's physical violence, right? Of course, with an observational study like this, you could specify anything, either one as the outcome or the predictor, right? But where the assumption that she's making is that there is some causal, that the domestic violence is coming as a consequence of the income and not the other way around. And so, yeah, and then, right, this outcome measure of domestic violence is just this binary yes no question, whereas income is something that's being specified in dollars, right? So what are, yeah, I think there's a number of right answers here depending on the assumptions that we're making. So yeah, so I see one answer of Pearson's R, which is definitely something we could do. Sorry. So Pearson's R would I think not work here because the outcome here is nominal, right? So for Pearson's R, we really need two different scalar measurements. So yeah, so there's one answer in chat here of two-way chi-squared, which could definitely be an option. So if we right, if we just for income, if we just like binarize people of like, are they below the poverty line, for example, right, or are they below median income or something? So we just say, are you low income or not, and then is there violence or not? Then we'd be in two-way chi-squared land. Yeah, that's right. If we had a different measure of violence like that was scalar, we could definitely do a Pearson's R. We could be over in rank sum land if we think about so I think the two sort of answers I was thinking of is one is if we go down this path, so we have that if we think about if we think about here, if we sort of flip it so that the money is an outcome and the yes no domestic violence group is a predictor, we could end up with a t-test here, right? So again, you could do it either direction. And so this would basically just we're testing to see whether is there a difference in mean income between the people that are experiencing domestic violence and aren't. The one potential worry here is that maybe mean income tends to sometimes be a potentially worrisome measure, that the income distribution is very non-normal with these weird tails to it. And so when we're dealing with incomes as income as an outcome, we often want to go down this ordinal path here. So we could be right over in rank sum world, which would mean that we're just asking whether the median income between these groups is different, right? And so that probably makes more sense. The problem is that, right, since income has this long tail distribution, what'll end up happening is that responses from, if there's a small number of people in our data set with very large incomes, then their responses are going to really dominate the answers here, right? That if there's a single person with a very high income that's experiencing domestic violence, for example, then that might make us not get a significant result here, just because that will raise the mean of that group to a very large amount. So yeah, so at least if we think about again, we can think about it either direction. If we think about the outcome here as income, then we could use these examples. We haven't actually, I think I was probably a little misleading when I set this up. We haven't actually talked about how to do it the other direction, which is that if the outcome is nominal and our predictor is scalar, then we'd again have to use other methods we haven't talked about that are, they're sort of like versions of regression, right? So here, right, for scalar outcomes, we're assuming you can only have scalar predictors, but there's other kinds of regression here besides Pearson's correlation. But at least of the methods we've talked about in this class, these are probably the most appropriate, or the two-way chi-squared, right? If we choose to binarize the income. Okay. All right. Thanks for sticking with me through all of those. I hope this gives you some sense for, right, that when we're thinking about how to apply the statistical tests, there are like sort of critical features of the data sets that are going to change where we go. But there's also a lot of decision making we have to make, right? So it's really not just a kind of statistics is not really just this like black box that we could run on any data. We have to understand what we're applying it to. We have to understand what assumptions are reasonable in this domain. Okay. So this idea of trying to understand both what question we're trying to ask as well as what assumptions we're going to make on the data. Of course, though, like in practice, if you're the one actually doing this research, this whole exercises we've been doing are a little bit backwards, right? Which is that we really shouldn't like collect the data first and then try to figure out what test to run. Ideally, we should do this the other way. We should think about what kind of test do we want to run? What kind of conclusion do we want to draw? And then we can think about how to actually construct an experiment that's going to answer that question, right? And so this idea of like a critical experiment, which is that the experiment we should be doing is the one that's going to help us differentiate between possible outcomes, right? If we want to decide between two possible theories, we want to make sure that our data can actually distinguish between the two of them, right? We want to figure out what kind of test we're going to run, and then figure out what kind of experiment can we run that's going to have the most power on this test, right? And so if we understand the statistics of how this works, this can help us do things not only like power analyses, but also think about, if we want to answer if we want to have a model that makes a continuous prediction, for example, we're going to have to collect that kind of continuous data in our experiment. So in some ways, statistics is the most useful when designing experiments, right? That in practice, often statisticians get brought in near the end of a project, but really that's what we'd like to do is think about the statistics at the beginning, right? So once we have an analysis plan, then we can really start then we can make sure we're collecting the right kind of data that we need for this to get a useful answer out of this. Right. And another thing we can do is make sure that if we are aiming to use a particular statistical technique that has some kind of assumptions in it, then we can try to make sure we satisfy those assumptions when we're collecting the data. Right. So, for example, all the methods we've talked about in this class require independent uniform samples. Right. So if we want to use one of these methods, we're going to have to think about how to design an experiment that at least approximately satisfies that assumption. Right. If our goal here is that we're going to want to do a repeated measures ANOVA, then we're going to want to think about how do I make sure that these groups, for example, have that the distributions within these groups are going to be roughly normally distributed. How do I make sure that the variances in these groups aren't that different, right? If we don't want to relax that assumption. And so there might be things we could do when we're designing the experiment to try to make these assumptions hold. Right. And so there's definitely a danger of getting lost in the woods a little bit with some of these advanced stats methods after we collect our data and then realizing we actually didn't collect the kind of data we need. And I mean, this fits into this whole idea of that the goal for each experiment is to make some predictions about what we're going to see and then run the experiment to find out. And so ideally, a lot of the research we are doing should really be confirmatory, which is that we have some relatively strong prediction and we can run the experiment and see if it actually pans out the way we predict or not. Of course, in practice, what ends up happening is that the current theory that we have either makes a wrong prediction on our data or it doesn't make a prediction for this circumstance at all, right? We're manipulating something that isn't a component of our current theory. And so this is really like most of what science is, right? Is thinking about how to modify these theories to actually get data that either allows us to evaluate whether it's correct or not, or makes our theory more in line with the data, right? So we can think about how to modify these theories, and of course this requires us to actually understand what the theories are, and we can make these possible predictions, right? So there's usually a big space of ways to modify our theories that could give different kinds of answers. And then once we understand what those differences are, then that's when we can run our experiments and run statistical tests between them. We've also talked about effect size in this class, which is something that often gets swept under the rug a little bit. But when we're designing an experiment, we really need to have some idea of what these this expected effect size is, right? So just saying that we expect this something to have an impact is a very vague statement, and it's something that makes it really hard to plan an experiment because we don't, for example, we don't know how sensitive our experiment needs to be and how big it needs to be. If we expect a small effect size, then that tells us that we're going to need to have a lot of data to be able to study this phenomenon. And so really what we'd like to have are theories that make testable predictions about effect size, right? That don't just say this is going to have an impact on this or this is going to be related to this, but the theory actually tells us something about like how big we should expect that relationship to be. And if we can't do that, we probably need to make our theories a little bit better. And if our effect size is wrong from our experiment, again, we need to think about that discrepancy. Is it something about the theory is wrong, or maybe something about the way we're measuring things is wrong? This is usually not the case for a lot of theories, especially a lot of theories in psychology really just say what we're just testing is like, does something have any impact at all on something else? And the problem with that is that, again, it makes it hard to design experiments. It makes it hard to know whether we've actually measured a reasonable effect size or not in our experiments. But so ideally, we'd be able to make these more kinds of sophisticated predictions. Okay, so I'd like to just sum up by just going through just 10 ideas that we've talked about throughout the class. And these are, just sort of written down as like sort of conceptual ideas that we've talked about, and things that apply to lots of kinds of statistics outside of the things we've talked about in this class too. So the first one is that good data is not just a collection of anecdotes, right? And specifically, a common thread across all of these techniques is the importance of random and representative sampling. Right. And this is, again, in real life, this is a big stumbling block. This is something we're going to talk about on Thursday as well. But it's important to remember that just getting lots of data, and these days we have some very large sources of data about all kinds of things, is not necessarily, it might be very difficult to make inferences from this data if we don't understand how it was sampled. Right? We can certainly do descriptive statistics on big data, but if we want to make inferences, we need to understand something about how the sampling from the population happened. Otherwise, there's just no way we can make an inference to the population from this data. Number two is that accidents happen and weird data happens, but accidents don't keep happening, which means that as we have more and more well-sampled data, we can have much less uncertainty about the statistics of our population, right? So we can measure these descriptive statistics in our sample. It's possible to get really weird and unrepresentative descriptive statistics in a small sample, but over time we should expect convergence toward the population. Number three is that probability theory is the best way to think about how we can describe uncertainty and talk about confidence. It lets us be very specific about what we don't know, and provides tools that let us see what we can conclude. And so, right, this is the basis for a lot of the Bayesian statistics that's becoming more and more popular. Is that a lot of our intuitions about what makes something probable or not are not that great. The mathematics of probability theory gives us a way for actually computing this. Number four is that uncertainty propagates, meaning that small noise piles up into big noise, small variances add up into big variances. So a lot of the techniques we use basically use the fact that uncertainty adds up in this way. And it also means that we can find ways to take it apart. So ANOVAs, for example, are all based in this idea that the variation in our data is coming from a sum of different kinds of variations. And if we can figure out the sources of those variation, that tells us something about how this data is actually being generated. Number five is that our estimate, when we're making inferences, our estimate is usually not going to be just a single number based on our sample, but a whole distribution of answers. Right. So, for example, if we measure a mean in our sample, that's just one of many possible guesses about what the population mean is. Even if it's the best guess, meaning it's the sort of most likely answer, we probably other guesses nearby are almost as good. Right. And so when we have a very wide confidence interval, which is often the case at least in smaller data sets, then then we really don't have any specific confidence about any one of these numbers. And really the outcome, the output of our statistical analysis is this entire confidence interval. It's not a specific number about our population. Number 6 is that a lot of these tests that we use rely on the central limit theorem, which is that the sampling distribution of averages is trying to become normal. Right. So anytime we're taking an average of a bunch of numbers, as the size of that bunch of numbers increases, this is going to look more and more normal. Of course, the operative word here is trying, meaning that only with really large amounts of data are these sampling distributions going to be exactly normal. Otherwise, we have to think about using more sophisticated things like t-distributions or permutation tests or things like that. Number 7 is that whenever we can, we would prefer to use repeated measures, right? That doing repeated measures, meaning looking at pre and post measurements on an intervention, for example, is a great way to get rid of a big source of uncertainty, which is that people, that there's variation across people, right? So if we can use each person as their own baseline, that helps us a lot in figuring out whether the thing we're doing actually has an impact or not. Unfortunately, we can't always use repeated measures. It's not always ethical, right? That maybe this is something we're studying something that we really shouldn't be putting people into groups, or it might just be impossible, right? Maybe the thing we care about here is something that happened in the past, for example. Our regression models, when we're trying to create predictors, we often want to use regression models than simply comparisons of means. That in general, a continuous predictor, as long as there's some meaning to the values of that predictor, is usually going to be a better predictor than a binary one. And of course, as we've also discussed a little bit at the end of the linear models class, is that almost all of these statistical procedures like t-tests and ANOVAs are really kind of regression in disguise, right? They're really equivalent to a regression prediction model. And so often in practice, we use these kinds of regression frameworks to talk about all of these methods. All right, and the last 2 is that small effects are much harder to detect and much easier to misestimate. And unfortunately, many of the things we're studying in psychology are relatively small effects. And so we have to think about things like, first of all, being skeptical about plausible effect sizes, that if an experiment shows a very large impact of a relatively subtle intervention, we should be a little suspicious about whether this could be a biased estimate of the effect size. Using larger samples to make it less likely that we just got a sort of outlier. And also being a little bit skeptical of studies when studies with small sample sizes report very large effect sizes. Right, small sample sizes are almost certainly likely to be underpowered for small effects. And if they do detect an effect, it's almost certainly misestimated. And finally, the best way to compare multiple models is to compare how well they fit to the evidence. This is something that we can't really do with traditional null hypothesis testing, right? Null hypothesis testing is really just designed to reject null hypotheses. It's not really good for comparing hypotheses to each other. Right. So these Bayesian approaches we've talked about are more naturally suited to this. They can say for each hypothesis something about how well it fits the data and allow us to compare between multiple possible explanations. So to sum up, a lot of figuring out how to apply statistics in practice is to think about all of these possible tests we could use and what kind of questions we need to ask about our data to figure out which is the right tool. We should be thinking about statistics at every stage of our science, from all the way from designing the studies to understanding the results of a particular experiment, all the way to doing meta-analyses of multiple experiments and developing theories from them. Often we only sort of think about stats at the end of an experiment, which could be too late to really get the kind of data we need. And really all of these kinds of all the things we talked about in the class really hinge on trying to understand uncertainty, right? That the main goal of what we want to come out of a statistical test is not really just a description of the sample, and it's not just a point estimate of an inference. It's trying to say something about how sure we are, how strong of evidence do we actually have to reject a null hypothesis or to compare multiple models. Right. And so all statistics is really about quantifying uncertainty, computing uncertainty, maybe drawing thresholds on when we think we're sure enough about things to reject them. Right. And so, right, that's why all of these methods are really, it's critical to think about what we don't know, right? What kind of uncertainty is there in our data? What kind of uncertainty is there in the null hypothesis we think we're sampling from? And that can help us figure out how confident we should be in our conclusions. All right, any last questions? All right. Again, try to get in labs and homeworks this week if you can. I'd recommend you do that before you start the final project, which is going out on Thursday. There'll be the final lecture on Thursday morning, which again is optional. The material won't be on the final project at all, but I do think you'll find it interesting, and so feel free to come on and ask questions as well. Great. See you soon.